to do it where the adjacent points don't vary perhaps in more than 1 or 2 bit positions. There are bad ways to do it where you could have a lot of adjacent points that vary in all 3-bit positions. Okay, and you'd have a higher n sub b when you do that. The nearest neighbor union bound for symbol error is independent of all of that. It doesn't depend on the specific bit mappings. The probability of bit error does depend on those bit mappings. So you can have 2 systems that have the same probability of symbol error but have different probability of bit error because of the mappings. So again, there's this question of perhaps fairness in evaluating constellation. And yes, sir. Little b is the number of bits. Sorry, I should remind everyone here. This is log base 2 of m, the number of points in the constellation. Okay, and I actually have an example in the notes that you're encouraged to look at where we make an assignment of bits to each of the points in that 8 AM PM constellation and then work through that. It's a lot of kind of algebra to follow how do you get the number of nearest neighbors, but I think you'll all be able to follow that, but it may help you just kind of get some confidence in computing the actual probability of bit error itself, and it is a little more tedious and detailed than counting nearest neighbors per se. Okay, topic B, fair comparisons. Well, this is something that's really a EE379 special. I haven't really seen it in other textbooks. Just based on my 25 years of working in the industry, some of it's been in the university, some of it's been elsewhere. This is an area that's really important, fair comparisons. And so I put this in and I try to come up with a method. I'm pretty sure it's solid at this point. I've been teaching it for about 5 or 10 years. That tells you how to make a fair comparison. And I have seen untold abuses of comparisons in the industry, some of which cost their companies a fortune just because someone doesn't know how to make a fair comparison. And the biggest example I always like to cite, it happened about 12 years ago when we were doing the original HDTV deliberations here in the United States. It was the first place that started looking at HDTV. And there were 2 companies that were battling out their major companies. Some of the I won't embarrass them by saying, but some of the biggest names in communications, and their top engineers were having a fight over 2 different transmission methods for HDTV. And one guy was insisting his method was 3 dB better than the other, and they were spending hundreds of millions of dollars having this fight, trying to line up other companies. And it was a mistake. He didn't know how to make a fair comparison. The 2 systems were in fact identical in terms of their performance, but you could not convince this guy, and actually started spending a lot of money on it. It became harder and harder to convince him because then he would have, his boss would have been mad about all that money they spent fighting this when the 2 systems weren't different. Eventually they found some kind of political way of pushing this under the rug, okay, and coming up with a compromise, and no one ever admitted they made a mistake. But it was kind of amusing to anyone who knew about transmission to watch this fight as it went on. And of course, anyone who tried to point out that there was a mistake there was immediately blasted as not knowing what they're doing, or some academic or techie that shouldn't be listened to. So with that as the intro, to hopefully attract your attention, let me provide some parameters that I think are important in making a fair comparison. The first one is data rate. Data rate is the number of bits transmitted, again, B is log base 2 of m, per symbol period, capital T. Okay, so it's going to be in bits per second. So one of the things we might want to do in comparing 2 systems is, of course, compare them at the same data rate. If we're comparing 2 systems and one is transmitting 100 bits per second, the other one's transmitting 10,000 bits per second, and they both have the same probability of error, we probably take the one that's transmitting 10,000 bits per second because it has a higher data rate. Not fair to compare 2 systems that have different data rates. Second quantity is power. Where the power P is the energy per symbol divided by the symbol period. Okay. One system takes more power, not really fair to make a comparison between two systems at different power levels. C, total bandwidth. And this really means over all the phi entities. So if you were to look at the Fourier transform of each and every one of the basis functions, what's the maximum frequency used? Or you could approximate it by saying, okay, it's small enough beyond a frequency. What's that maximum frequency used in the system? Let's call that W. And usually it's some kind of positive bandwidth W that we'd be looking at in a real system. You could count negative frequencies and then all bandwidths are doubled. When we do that, that's fine. But we'll call it W. We'll say it's a positive bandwidth. D, the symbol period. Even if I've got two systems, use the same bandwidth, the same power, the same data rate, if somehow one is using longer symbol periods, okay, it may come out in the data rate power comparison, but let us say that they really should be using, it's kind of like bandwidth. You can get more basis functions if you have a longer time interval. So that should perhaps be the same also. And then finally, probability of error. PE or PB bar if you want. So those are the things we have to work with. Now if we held 4 of those things constant and compared the fifth, I say it's a fair comparison. Take any 4 of the 5, hold them constant, compare the fifth, it's a fair comparison. Okay, so now you can see why people sometimes make mistakes. If you've got all these quantities to keep track of, one of them slips out on you. In comparison, that's how you can make a mistake. It's in fact exactly how the mistakes are made. Hold 4 constant, compare the fifth, and you'll have a fair comparison. Now that may usually be the probability of error, but it doesn't have to be. I'm going to reduce the 5 to 3. Okay, how am I going to do that? Yes, sir?
Just a quick question about how that, given these five metrics, which seem to relate to comparing just the constellations themselves, how does it typically work out that these 5 metrics are equivalent when you actually go a little bit further and compare how the individual constellations are actually implemented?
Let me see if I got that question. Could you ask that question again? There was a kind of something that didn't logically follow. It could be just I didn't hear it right.
So this seems to be comparing 2 given constellations.
Yes.
Once you actually, typically does it end up actually holding true once you actually go towards implementing these 2 constellations?
This includes everything, not just the constellation, but the basis functions, the implementation itself, on an additive white Gaussian noise channel. Okay, reduced to 3. Okay, well, the observation I take advantage of is that the number of dimensions that we can squeeze into a given bandwidth W, positive bandwidth W, and a symbol period T is given by the following expression, 2WT. It's not too hard to convince yourself that that is true. If I were to take a basis function in time that looked like this, where it went from 0 to t, so this is phi 1 of t, then its Fourier transform, okay, this is going to be some kind of sinc function, and basically it's going to go to 0, which is kind of the important thing here, at minus 1 over 2t, and 1 over 2t. Just trust me if you do the sinc function calculation correctly, and in fact, it's going to bounce around. So the bandwidth of this system is basically about 1 over t. So if I were to take a certain bandwidth, a certain time slot 0 to t, and I were to look at its positive bandwidth, it's 1 over 2t. Okay? And basically I can get one basis function, okay, in that interval. Now you can play with more bandwidth, okay, hold t constant, and you can squeeze more of these sinc functions, if you will. Or if you can hold the bandwidth constant, you could put more of these in the time domain, and they would all be lining up in frequency with offsets so that they essentially don't overlap with one another. You'd be able to recover the waveforms. Or you could fix this, call this frequency f here, call this capital F, and then what you're going to have is a 1 over 2f here and 1 over 2f there, and basically you have a bunch of sinc functions in the time domain, and if you're sampling at multiples of the symbol rate, they won't overlap with one another. So you can squeeze that many basis functions into a positive bandwidth of W, and a symbol interval of capital T is 2WT. Now this is a well-known result. It's kind of an approximate result. There are some theories of how to get more basis functions in a given amount of bandwidth and a given amount of time. If you're really up on information theory, you may have heard of something called the prolate spheroidal waveforms. And they're a set of functions that basically get, set of basis functions basically get this number, this 2 here, up to about 2.2 or so. And what happens is they're not completely orthogonal, the basis functions, but they're almost orthogonal. They have a very small deviation. If you take the inner product between the functions, it's below epsilon. You define the epsilon and you let it go to 0, you can basically come up with this limiting set of functions. It's very complicated to describe. And you get 10% more basis functions that way. Here we can just kind of simply do it, either chopping up time or chopping up frequency. This is the number of basis functions that you can get in a given amount of frequency and a given amount of time. So I look at dimensions as a more appropriate measure of a system resource, which could be allocated in time or could be allocated in frequency. And in fact, the product of the two tells me the number of dimensions. And that's truly the measure of resource. That's where sometimes we get in trouble because we're using a system that has more bandwidth, but it operates over the same time interval. It has more basis functions. It may look better in terms of its performance. Not fair, okay, because it's got more bandwidth. So what we're going to do is we're going to hold constant the number of dimensions used. Take them in frequency, take them in time. Since time and frequency are essentially equivalent to one another, if I double either one of these, I can double the number of dimensions I get. That is a fair comparison. And so what I do is now, instead of having data rate up here, which is divided by t, not so fair. You see I'm holding the bandwidth constant here on the third quantity, and I have bandwidth. Well, they really are measures of system resource. So what I'm going to replace both of those by is bits per dimension, B bar. Okay. And it's essentially bits per system resource that's being transmitted. Second thing, instead of power, using that same trick, I'm going to have energy per dimension, EX bar. Because I have here power, energy per time, but it's kind of an unfair comparison if I'm using more bandwidth and I hold time fixed. So what's more fair is to divide by both time and bandwidth. That's energy per dimension. I have bits per dimension, energy per dimension, and then finally, as we saw a moment ago, the probability of error per dimension, PE bar. And so I took the 5 quantities above, and you can see it's in there. I've got W and T, and I've essentially eliminated both of those by dividing them into the rate and the power. Now what can happen is I hold 2 constant and compare the third. And that is a fair comparison. for the additive white Gaussian noise channel. Again, it's usually PE bar that gets compared, but I hold now bits per dimension constant, energy per dimension constant. I don't care what the data rate is. I don't care what the power is. What I care about is B bar, EX bar. If those two things are the same, I can compare the PE bar. And that will be a fair comparison. You won't make mistakes like the HDTV mistake that occurred earlier. So it always works. Now let's give an example of how and why this can be used and why it should be fair. The example is going to be a system that has a data rate of 10 megabits per second. So R is equal to 10 megabits per second. And we're going to have two systems that achieve this 10 megabits per second. I have a system 1 where I have a basis function which has a Fourier transform, single basis function, Fourier transform, phi of f, that looks like this. It goes from minus 5 megahertz to plus 5 megahertz. And I'm going to transmit plus or minus 1 as the signal levels for a binary transmission system. Okay. If you do invert this Fourier transform, the basis function of the time domain will be a sinc function, and it will go to 0 at all non-zero multiples of the symbol rate, 10 megahertz in this case, and we'll get 1 bit per symbol, so we get 10 megabits per second. Okay. The W in this case is clearly 5 megahertz. And the signal constellation looks like this. System 2. Is going to have two basis functions in it. The first one is going to look just like this one above, phi 1 of f between minus 5 and 5 megahertz. But phi 2 of f is going to look like this, where it goes from 5 to 10, positive frequencies here, and from minus 5 to minus 10, negative. Clearly, those two basis functions are orthogonal. They both have the same bandwidth, each of the basis functions of 5, but the overall W in this case is 10 megahertz. And I transmit with a constellation, now that I have two dimensions to use. Let's put the points diagonally opposite, say like that. This point is 1, 1. This point would be minus 1, minus 1. I've used a different basis function for the second dimension. Okay. Now system 2, if I look at these two binary transmission systems, each one clearly has one nearest neighbor, and the minimum distance here for this system, d min, is equal to 2. And the minimum distance for this system is 2 root 2. Okay, square root of 2 better between these 2 points. Okay. Pardon? Because the number of messages I'm transmitting here, well, I didn't quite say yet here, but the symbol rate here is 10 megahertz for this basis function. It's also 10 megahertz for this basis function. So I'm still transmitting 10 million times per second, only 2 points. Right? So that's 10 megabits per second. So the data rate is the same in both systems. I should have said that, but that's why only 2 points here. So I have two 10 megabit per second systems. This one is, they both have the same data rate. This one looks like it has a bigger minimum distance. The power for these systems kind of looks the same, okay, because I've got the same symbol period, and I've got well, actually, if I look at this system, I have an EX. Here, the symbol period's the same. It's 10 microseconds, and the energy, okay, for a symbol. Now, if I look at the energy for a symbol, okay, we're starting to see, well, I got a 1 and a 1. Okay, so I got more energy per symbol. Now I got an energy of 2. Now, this system otherwise might be otherwise, because it's playing at the same data rate, it's got the same symbol rate, okay, but it looks better. Now what's happening is I'm using extra system resource here. Got more bandwidth, and also because of that, I have more power being transmitted in the system. So this is an example of a way of making a mistake in transmission. It's not evident by, well, the data rate's the same. What's going on? Bring the boss into the lab. He may not even realize you're using double the bandwidth to get the extra performance improvement. Now, how to avoid this? We look at the EX bar. We look at the B bar.